It is recording. All right, my friends. I had forgotten to tell you. Well, that's partially true. The real truth is that I've been trying to put this off and not even think about it, but I can't do that any longer. Mr. Hevel and I have been taking turns going to chemistry meetings that the district holds, and it's my turn. And I am sorry about this, but I have to be out on Monday. I just kept knowing that it was coming up and putting it off and not really thinking about it. But now I don't have a choice. In fact, I haven't even put my sub-request in yet. But I need to do that because Monday I won't be here. We are going to still have something hanging in the chapter. We have our quiz on Tuesday, and we still have to do that. I am going to... I'm not sure what I'm going to do. I may just record Monday's lesson and have you watch it during class. Maybe Mr. Hevel will come in and lecture the rest of it through. You can ask questions, yeah, definitely. Yeah.
So, when you have Mr. Hevel come in, is he help get started?
Do what?
Do you have Mr. Hevel come in and ask Mr. Hevel have a
We might. We've done that before too.
Yeah, don't procrastinate.
Good lesson. Yeah. That's right. All right. Can I have your cooperation too? I am recording this hour, so sorry about that. Anthony over there.
Wait, what?
Wait, what? Here we go again. This is our third hour too, and there's some goofballs in the class.
Hamza, Noor.
Yeah. Hamza, Noor. That's true. The goofiest of all.
Justin Dane.
No, you.
Here's where we were yesterday. We came up with this very important concept in chemistry. If delta G is negative, that means the reaction is going to be spontaneous. Now, I'd like to begin today with an example that you can find in the book, but I think this is worth walking through and making sure that we understand some really foundational things about delta G. I have as an example a physical change, solid ice changing to liquid water, ice melting. You're given the delta H and you're given the delta S. Now there's a couple of things that make this a good example. The most important thing probably though is the fact that you're familiar with this. And so when we talk about it, ice melting, we can understand that. We're going to use this. Delta G equals delta H minus T delta S, the Gibbs free energy equation. The delta H, as you notice, is positive. Is it favorable for matter to gain heat? No, that's not favorable. In fact, I'm going to go ahead and write that out here. Not favorable. The delta S is positive. Is it favorable for matter to become more random or disordered?
Yes.
Yes. So we have one quantity going for us and one not going for us here in the melting of ice. I use those terms favorable and unfavorable often in here. I mean, if our goal is to have reactions occur, then there's two factors that contribute to whether a reaction is going to occur, and it's those two. And so if they're both favorable, that means the reaction will occur. But if you have one of each, like we have here, it's going to depend on what the temperature is. I'm going to ask you to calculate the delta G under 3 different temperatures. And we're not going to do all 3 at once, just do one at a time. Let's take a look at the first temperature, negative 10 degrees. Ready?
Can't you just solve for G in terms of T, right? And then just figure out when G is negative for that?
Yes. Yes, you could. But just chill out with me. I want people to conceptually understand what delta G means. And yeah, we could set it less than 0 and find where delta G is negative, but just watch what happens. I think you'll like it. we have an environment of negative 10 degrees, maybe we're in some cooler and we have a block of ice at negative 10. The question is, will the ice melt? Calculate delta G. We have this delta H and delta S, and we have this formula. So delta G would equal delta H, which is 6033 joules per mole, positive that is, minus the temperature, which is negative 10 degrees. It's not a delta T, it's a T. Anytime you have T, you use Kelvin if you need to calculate with it. So negative 10 is 263 Kelvin times the delta S. And by the way, usually delta H is in kilojoules and delta S is just in joules. So you do need to change them into the same unit. I've gone ahead and done that just to make our work simpler. And so I don't mess up. Positive 22.1 joules per mole Kelvin. The Kelvins cancel out in the equation, and so we're left with joules per mole subtracting the same unit. That's good. When you grab a calculator, if you have one out, crank that number up. All right, so we're allowed 3 sig figs. 221. Positive joules per mole. What does that tell us? That means it's not spontaneous. The delta G that we calculated means that if we're in a cooler or in an environment, maybe it's outside and it's very cold in the wintertime and it's negative 10 degrees, that ice will not spontaneously melt. We have experience with that. Do you see ice melting at negative 10 degrees Celsius? No. It doesn't melt. It stays solid. So in the direction that it's written, it's not spontaneous. Now, if we had the reverse possible, if I had liquid water and it was at negative 10, would it spontaneously freeze? Would the reverse reaction occur spontaneously? Yeah. If we're at negative 10 degrees Celsius, imagine being outside in the wintertime is negative 10 Celsius. It's cold, very cold. We got our jackets on, we have a sample of water. Does the water spontaneously freeze? It turns out yes. If you have a reaction that's non-spontaneous in one direction, it will absolutely be spontaneous in the other direction. Yes?
What if delta G is 0 for that reaction?
We're not going there yet. That's the next thing. That's the next thing. Understanding that spontaneous in one direction, not spontaneous in the other, that right there is very important. I had something else to say about that. I don't remember what it was. It'll come back to me. So let's go on and do the next temperature. The next temperature would be the melting point of the solid. 0 degrees Celsius. Calculate the delta G at 0 degrees Celsius. It's going to look like this. Delta G equals the same delta H, 6033. Joules per mole minus 273 times 22.1. All right, and that calculation is going to give us something that's very close to 0. You get like 0.3, negative 0.3, right? 0.3 joules. Now, I do have to tell you that a joule is a small unit. So we have this little tiny number of small unit. Is this close enough that we can call it 0?
Yeah.
Can we please? Yeah. Just call it 0, it's close enough. So we're going to get that big fat goose egg. What physical meaning does that have when the delta G is 0? Ready?
It's not spontaneous either way.
Yeah, it's not going to be spontaneous that way, and it's not going to be spontaneous that way. So if I have ice, solid ice, and I have a cooler that is specifically geared to operate at 0 degrees Celsius, will my ice melt? Nope. Just sits there as ice. And if my friend walks into the cooler and they have a beaker of water and they set the beaker down, we watch the beaker. will the beaker of water freeze?
The ice will melt. No.
Yeah, because you walk it right to the system.
Oh, Venky. Nope, it's a good cooler. Doesn't change temperature. Peter?
If you put the ice into the water.
If you put the ice into the water and the conditions are 0 degrees Celsius. The ice is at 0 degrees, the water is at 0 degrees. Is there a transfer of heat?
No.
No.
It'll just sit there as ice water. When your delta G is 0, that is a condition that we call equilibrium. There's no push for the reaction to go that way, and there's no push for the reaction to go that way. The reaction is what we would consider at rest. It's an equilibrium. That's it. So equilibrium condition exists when delta G equals 0. You can have equilibrium between two phases. Definitely you can. The other thing that I had forgotten that I did want to mention was this. Remember, I mentioned this yesterday. Spontaneous does not necessarily mean fast. A reaction can be spontaneous but take a long, long time to complete. And I'm not saying that at this temperature, -10, like it's spontaneous, the liquid freezing at -10 is a spontaneous process going this way. That doesn't mean that the liquid instantly freezes. It might take a while. You know, you've gone in and put ice in the freezer before. If you come back 5 minutes later and look at your ice, it's not ice yet. It's still liquid water. It hasn't frozen. So it eventually will, spontaneously, but it is a slow process. And so remember that. The spontaneous does not mean fast. It doesn't mean instant. It will happen. It just might take a while. Yeah.
Unrelated question. Why does hot water freeze faster than cold water?
It has to do with Newton's law of cooling. You get that curve going, and it's like a decay rate, I think. It cools faster when it starts at a higher temperature.
If it's like boiling, and then you just take it out and put it in the freezer, it cools faster.
It'll cool faster, yeah, than room temperature water would.
Well, it's like adding the energy back out to the system and all the surroundings. You add the amount of energy to it. That's Mark over here. I thought he's going up to the front, like, energy goes to the surroundings and makes it like a low temperature, makes it a bigger difference.
Yes. But it does cool faster. And the rate of cooling does make a difference. Yeah. All right, now if you will, please just humor me. And let's go through the delta G calculation when we're at +10. Let's do this. Go ahead, quickly.
Can I guess what it is?
What?
Can I guess what it is?
Yes.
Minus 221 goes for
It is -221, that's right. Yep, yeah. So the delta G is 6033 minus 283. I'm leaving the units out of this because we've done it enough. +221 joules per mole. No, I just said that wrong, didn't I? That was positive. It's -221. And that means that at +10 degrees, solid ice spontaneously will melt. Again, it doesn't melt instantly. It doesn't poof go from liquid to from solid to liquid. It takes a while, but it spontaneously occurs. Here's another. Go ahead.
I think it means like it starts spontaneously, right?
Yes. And it will go to the end, to completion, spontaneously. Another thing that I wanted to mention too about this first data point we had, when we have a -10 degree temperature, if we're at -10, that solid is not going to melt under those conditions. Is there something that we can do to ice at -10 though to get it to melt? It's got to stay at -10.
You decrease the pressure.
We change the pressure of it. Actually, you have to increase the pressure of water. Because water expands when it freezes. So if you compress it, like ice skaters, they say that the ice skate will, because of the pressure on the ice, actually melt the ice onto the ice skate. So this reaction at -10 is not spontaneous. However, we could do work on the system to get it to occur. And that is important to know about non-spontaneous reactions. It doesn't mean that it's hopeless. If you have a reaction that you really want it to work, if it's not spontaneous, you could do something to it to get it to happen. It just doesn't happen on its own.
Like lower the temperature? Or raise the temperature?
No, we're talking about at the same temperature. We have to do work on it to get it to occur, is what I'm saying. Yeah.
If you had like a single replacement action or like reaction, couldn't you just like keep taking the product out and just keep pushing it into like?
Yeah, and we're going to talk about that when we do equilibrium. Yeah. Now, again, that's Le Chatelier's principle. You were talking about that yesterday, the day before. Yeah. Mark, you got one?
So I have an idea.
Okay.
If you're gone on Monday, if you're gone on Monday, why don't we just have a start with this class and then have a start with this?
Dude, somebody said that already.
Well,
It's a good idea.
Tell him, maybe shit.
Yeah.
Well, it is.
Great minds think alike. Mark and Hank.
It is.
Oh, no.
Congratulations, you're elite like Hank. All right.
I don't think he wants to.
All right. Now this, I know there's a lot of words on this thing, but oh man, there will be a test question that has to do with this. At least one.
Yes.
You've got to know it. So these two terms affect delta G, which is ultimately what determines whether something is spontaneous. So we need a negative delta G. So we need the delta H and the delta S to provide for a negative delta G if we want a spontaneous reaction. Yes?
Isn't the like spontaneous at both temperatures like pretty subjective?
Yeah. You could determine what the temperature is.
Yeah, but that temperature could be really high, right?
It could be really high, yeah.
Like if it was like water boiling or something, that could be really
Yes. If the delta H is a, let's see.
or water condensing together.
So this term is favorable and that term is not favorable. So if the delta H is a really small negative number, that's favorable.
Or we just have delta S be really, really large.
Yeah, if delta S is really large.
Then T is
Yeah. No, yeah, I'm getting tripped up too. This is the not favorable term. So if this term is really big and negative, then you need a high temperature to cause this to dominate. Don't worry, just write what's on the board. Don't think like Freddy.
Well, no, it's the other way around because that would make delta G positive.
Yeah.
Which would be non-spontaneous.
So
If you have a big negative delta S, that's where you need a high delta T. No, I'm wrong about that.
you need a really small delta S, like a really high delta H, and then you can have like a really large T, and it still wouldn't be spontaneous.
Yes, that's right.
Wait, the last one is spontaneous at negative temperatures. I don't think they get
The inside-out motion.
Yeah.
Yes.
Wait, did you tell your other out?
No, you guys are special. Okay, now I'm trying not to talk while you're writing. If you have a negative delta H, that's favorable for the reaction. If you have a positive delta S, that's also favorable. So when both those terms are favorable, if you got a negative that number and a positive that number, remember the temperature's in Kelvin's got to be positive. So any temperature is going to give you a negative delta G. That's what I mean in that first line. A negative minus a positive is just going to cause the negative to become more negative. So delta G will certainly be negative. Now, if this second line, if delta H is negative, that's favorable. But delta S is negative also. That's not favorable. Then if we want a negative delta G, then we need the delta H term to dominate. The favorable term needs to dominate, and that means we need this term to be in low. That's what I'm talking about, low temperature. In the next slide, or next line, this term is not favorable, but this is favorable. So we need this term to dominate, so that's where I get the idea of a higher temperature. When you have a positive and a positive, that's not helping delta G to be negative, but this is, so we need that term to be big. So the higher the temperature, the more negative the delta G. Yeah.
What do you mean by like favorable or not favorable?
You know how when we were talking about enthalpy, the delta H, I talked about how matter is more stable. It becomes more stable when it can give off some of its heat. That's favorable for matter to get rid of some of its heat. It's also favorable for matter to become more messy. So matter tends to become the most stable and give off the most energy when that's negative and that's positive. That's illustrated mathematically by the delta G term. We learned that delta G has to be negative for it to be spontaneous. And for it to be spontaneous, that means that these two numbers have to work out mathematically to give you a negative answer. So if the delta H is negative and the delta S is positive, then no matter what the temperature is, you're going to get a negative delta G value. Because you're taking a negative number and subtracting a number from it and making it more negative. So the most favorable condition is to have this term negative and this term positive. If you want a negative delta G, which we do because we want reactions to happen spontaneously, that's what's the most favorable. So what I'm saying is, well, if you have one of the two that are favorable for the reaction, well, can delta G be negative? The answer is yes. In this case, when they're both negative values, you need a small temperature so that this term can dominate and get you a negative answer when you subtract. And now we have both positives. This is not favorable. That means the matter has to take in some heat. Nature doesn't tend to want to take in heat. It wants to get rid of heat. That's not favorable, but this is. So that means we need this term to dominate, where this is kind of working against the delta G, so we need a high temperature to make the reaction spontaneous. Wait. What?
I have a question.
Okay.
So ice melting is endothermic, right?
Yeah.
Okay.
Yeah. That's why the temperature matters. All right. Now let's look at this. Where delta H is positive, that means it's taking in heat. That's not favorable. Delta S is negative, means it's becoming more ordered. That's not favorable. That process will not be favored at any, or not occur spontaneously at any temperature at all. That takes us back to what we talked about a couple of days ago, or yesterday maybe. If you have CO2 and water, and you want to make like gasoline and oxygen, you can't take a mixture of carbon dioxide and water to any temperature, low or high, and make gasoline and oxygen out of it. You ever make gasoline out of CO2? No. Can you imagine if we could make gasoline out of CO2 and water? We would not be paying $2 at the pump per gallon. It would be very, very cheap to do that. We would not have to mine fossil fuels if we could make gasoline out of CO2 and water, right? But however, unfortunately, it's not spontaneous to make that.
Can you use a catalyst to start a reaction?
It's not, yeah, even if you want to try to start it, it's not spontaneous. You have to pour a whole lot of energy into it to get it to happen that way. Now, plants do that. They don't make gasoline. Eventually, it changes to gasoline. But plants take these two things and make sugar. But it takes sunlight. It takes energy to do that. We haven't figured out how to do that effectively without the use of plants. I mean, plants are good, and we could, if we were in a pinch, we could make ethanol and grow our own fuel. But it is better to have a spontaneous process where you don't have to pour so much energy into it. All right, So in this bottom part down here, we can find delta G just like we found delta H, using Hess's law or using the table in the book. Or, now for delta G, you could also use that equation. Anybody have any other questions about that? Know this, and try not to just memorize. I know some people just memorize stuff, but try to understand how the nature tends to want to give off its energy, so it's favorable to have a negative delta H, favorable to become more random or disordered. And what these temperatures have to do with it. All right, I'm not going to have you actually do this problem, so don't start writing it down. I just want to mention it. This is the same exact two chemical equations we had last chapter, where we calculated the delta H for the reaction. This is the delta G, and it's showing that you can use Hess's law. It turns out that the delta G change, when diamond changes to graphite, is negative 3 kilojoules per mole.
Wait a second. So,
What does that say about this reaction? Sound look right to you?
No.
No.
Yeah.
Girls, I thought we've heard that diamonds are forever. Yeah.
Is it spontaneous to pressure is like backslash to
Yeah, spontaneous means at the current conditions. See those degree signs up there? That means 25. At 25 degrees, diamond is going to change to graphite spontaneously. So, is chemistry wrong? Or does this really happen? If it had a catalyst, it would go faster. The answer is, yes, it does happen spontaneously. Diamonds are not forever. However, remember that spontaneous does not mean fast. And it might take 1 trillion years for that to happen. For a half-carat diamond to change into graphite, it might take a long time. The reason that it takes so long, we're going to talk about in next chapter. If we looked at the energy, you don't have to write this down. We're going to get into this a lot. And I guess the reaction progress, which is that. Here's the reactant amount of energy, how much energy is stored. And here is the products. Notice the products have a little bit less energy. This thing was able to give off some free energy. That makes it spontaneous. The problem and the reason this doesn't go fast is because the activation energy is like through the roof. A diamond would have to gain a whole lot of energy in order for it to start to occur. You know how I talked about yesterday, that mixture of methane and oxygen, you have to give it a spark to happen? That spark, that means it's got a low activation. You give a little bit of a boost. You'd have to give this a big boost to get it started. So that's the barrier that it has to go through just to make that little change. It is spontaneous, but you got to give it a gigantic boost to happen. On its own, I don't even know what the activation energy is for this reaction. I just know from my experience in life, been around for 40-some years, this does not happen to this in my lifetime. My mom still has her wedding ring. She's been around, married longer than I've been around. And her diamond hasn't changed to graphite. So, yeah.
So how do we know if this happens on Jupiter? Jupiter temperature is like huge, except for there's too much pressure, so it might not do that.
Yeah, that would be different conditions. But look, I got that degree sign. That means standard conditions. Yep.
Well, is there
Yeah, if you had different conditions, this reaction might be spontaneous. Or I shouldn't say, it is spontaneous. It might be faster or whatever. Yeah.
Could it be the other way around?
It might be because the pressure is large enough.
So if it's spontaneous in this direction, that means it's not spontaneous in this direction. You're going to have to do a lot of more work even to get it to change that way. Because it's going to have, look, it's lower here. It's got to go through the same barrier that's even higher of a climb than this direction is.
But it's only 3 kilojoules.
Still higher. So it's even less likely that the graphite would change to diamond than the diamond would change to graphite. Anthony?
What are standard conditions?
Yes. Oh, what are standard conditions? I thought you said under standard conditions. 3 things, standard conditions. 1 mole and 25 degrees Celsius. So you got quantity, quantity, temperature, and pressure is 1 atmosphere. standard conditions. And we're going to find when we do the battery chapter, if you have solutions, it's 1 molarity too. So either 1 atmosphere for gases or 1 molarity for solutions.
Isn't that 0 Celsius? Like 273 grams.
No, thermodynamic standard conditions is 25 degrees Celsius. For gas laws, standard is 0 degrees Celsius. I hate that.
Yes.
We're going to move on to something else. We have about 20 minutes left in the hour. I got a derivation that's going to take us the last 20 minutes. Did I just say that, Carthy? Carthy, why do you hate so much?
You could just give us.
I know, and I could. I could just say, okay, use this equation. But you're advanced students. I want you to see where they
I
come from.
understand like why you write it, but that doesn't mean I have to write.
I understand. And I appreciate that. I think that's true. And it would save a lot of time and frustration to just not derive. But I don't know. We have to. I can't not do it. I hope that you're not counting particles. If you are, you would find that there's the same number of particles in here, here, and here. So either you count particles or you trust me. Stop counting, Freddie. I see what you're doing. There's 10 particles in each one. Which one has the most entropy?
Last one. Biggest one.
Why? That's right, but why?
Most disorder.
There's more ways that particles.
Yeah. There's the most disorder. There's the most possible arrangements